So digital filter frequency response. Anytime you have a filter, the basic idea of the filter, of course, is that it stops some frequencies and it allow other frequencies to let go or to pass through the system. And unless you plot the frequency response of the filter, you will not know what type of frequencies, what frequencies are stopped and what frequencies have been let go. So if you're designing a low pass filter, high pass filter, band pass or band reject, you will have to confirm that your design is correct by plotting the response of the filter. So when you're designing the digital system, then your response, of course, is your system design is given by h of z, right? So how to go from h of z to the frequency scale to plot the response? And it is very simple, and it is shown right over here. You will see all the markings over here because I've recorded this video and somehow the program stopped and didn't record anything. But anyways, so if you convert, if you want to go from z domain to the frequency domain, which is omega in radian per second, or frequency in hertz, cycles per second, and of course omega is 2 pi f. So if you want to go from z domain to omega domain or f domain, then all you have to do is you do z is equal to e to the power j omega ts, right? J omega ts. So you go ahead and substitute in your transfer function, you substitute wherever you have z, e to the power j omega ts. Ts is the sampling time and omega is 2 pi f, right? Now since Ts is constant for a system, then we define a normalized frequency uppercase omega as omega times Ts, and we define z is equal to e to the power j uppercase omega. Okay, and omega of course is 2 pi f, so 2 pi f Ts, and Ts is 1 over fs, so 2 pi f over fs. So the relationship between omega and f is that omega, uppercase omega, normalized frequency is 2 pi f over fs. Alright, so what is the range of omega or f for which you should plot the frequency response, calculate and plot the frequency response? Now if you go back to discrete Fourier transform discussion, in discrete Fourier transform, when you calculated the transform, you plotted the amplitude spectrum, phase spectrum. And now remember, the properties of discrete Fourier transform were that the DFT is periodic in nature with the periodicity of n, that is it goes from 0 to n minus 1 if you are plotting against the harmonic scale k, and if you're plotting against the frequency scale f, which is k times delta f, then the frequency one cycle is 0 to fs, right? That was the property, one of the properties of DFT. The same property holds for h of ej omega. That is, if you're plotting the and h of ej omega is a complex number. H of ej omega I'm referring to when you replace z by ej omega, right? That's a complex number, and it has magnitude response and phase response, right? So the property of DFT, that it is periodic in nature with the periodicity of fs, that is the response goes from 0 to fs, is valid for e to the power j omega as well. That e to the power j omega one cycle will also go from 0 to fs. And again, if you remember that the one cycle, basically you can define completely all the frequencies from 0 to fs by 2, which is the folding frequency or Nyquist frequency, and from fs by 2 to fs, it is just a mirror image of whatever spectrum you have from 0 to fs by 2. The same is true for e to the power j omega. That is, if you're plotting it against frequency f, then your complete frequency response can be determined from 0 to fs by 2 And from fs by 2 to fs, it is going to be just a mirror image of the frequency response. So let's say you have a low pass filter. So low pass filter response is something like this, right? Now, if this is your digital filter response against, and you're plotting it against frequencies, then it is going to go from 0 to fs by 2. That's your complete response. And if you go from fs by 2 to fs, that's going to be the mirror image of that. So it's going to go like this, something like this, right? But remember, this does not mean that it is a band stop filter. Apparently, you will see and you will say, hey, this is a band stop filter because it's stopping this band of frequencies. But this is not band stop filter, because the response will be determined from 0 to fs by 2. So whatever you see from 0 to fs by 2, that type of filter it is going to be, and that is a low pass filter. All right, going back to that. So the complete response can be determined from 0 to fs by 2. And if you're plotting against uppercase omega, so if you replace f by fs by 2, then of course fs will be cancelled out by this fs and 2 will be cancelled out by this 2. That means your complete response on the scale of omega can be plotted from 0 to pi. All right, so this is the range over which you can plot the frequency response. All right, this is all the explanation that I just verbally told you. Again, it's periodic. It has the same properties as DFT is periodic with periodicity of omega 2 pi, or f is equal to fs. And since it's a complex number, h of g omega is a complex number, then it has the magnitude of the complex number, that will be magnitude response versus frequency, and the phase of the complex number, which will be the phase response of the versus frequency. So it you can have two responses. Magnitude response is going to tell you if it's a low pass, high pass, band pass, or band stop filter, and phase response is going to tell you basically that if the phase is linear or non-linear in the band, whatever the filter pass band is. Magnitude response has even symmetry and phase response has odd symmetry. That is, if you are plotting the magnitude response on the positive frequencies and negative frequencies, then it will be the same. So if at 100 Hertz, you will have the same magnitude response as negative 100 Hertz. As far as phase is concerned, at 100 Hertz, if your phase is 20 degrees, at negative 100 Hertz, it's going to be negative 20 degrees. That is, it has the odd symmetry. And again, you have to go from only 0 to fs by 2 to determine the complete response. Okay, how do you do in the MATLAB? So these are these are 6 steps to plot the response in MATLAB. First, you define the range of omega from 0 to pi. So 0 initial number, pi final number, and then the period or step size. And usually I take 100th of the final number, in this case pi over 100. So you're plotting 101 points basically, which are usually good enough. You can plot 1000 point, doesn't matter. The reason that you're plotting good number of points is that your plot is going to be smooth, and you will not lose any information when you're plotting the response. Then you're going to define z is equal to e to the power j omega. Since omega is already defined from this, then it's going to calculate e to the power j omega and assign all those values to variable z. And then you're going to write down h of z using array-wise operation. What do we mean by array-wise operation? So if h of z is, let's say, z square plus 2z plus 1 over z cube plus z square plus 3z, whatever. So remember, for array-wise operation, you have to put a period before every power sign, every multiplication between the vectors, and every division if you are dividing a vector by another vector or a constant by another vector. So if you're writing this using array-wise operation, then it's going to be z period square plus 2z. You don't have to put a period over here because 2 is a constant, z is a vector, plus 1. And then you're going to put a period over here because the denominator is a vector as well and the numerator is a vector as well. Period divided by, again, z period cube. You're going to put a parentheses here, plus 2 plus z period square and stuff like that. Alright, then you're going to determine the magnitude response once h of ej omega is calculated in step number 3. Then you're going to calculate the magnitude response, which is basically, it's a complex number, so magnitude response of a complex number is square root of x square plus y square. But in MATLAB, you can use absolute function to calculate the magnitude response. And then you're going to determine the phase response. Again, phase response of a complex number is determined by, or phase of a complex number is determined by tangent inverse of y over x. In MATLAB, you can just use angle function, and angle function gives you phase in radians. So make sure multiply by 180 divided by pi in case you have to, or actually you always have to determine phase in degrees. So always multiply by 180 divided by pi. And in case you have to draw it against frequency in hertz, not omega in radians, then basically use the relationship that we discussed earlier, and then f is equal to fs over omega divided by 2 pi, and then plot against the frequency. Let's look at an example. This is a filter. Difference equation is yn xn is equal to xn minus 0.8 xn minus 1 plus 0.5 xn minus 2. Now, since there is no previous instance of y, it is an FIR filter, finite impulse response filter. So first thing you're going to do is you're going to take the z transform of both sides, and you're going to calculate what is h of z. And once you have h of z, once you have this equation right here, if you are using MATLAB to plot the response of the system, that's all you need. You're going to take this equation, and you're going to go up, and this is step number 3. That equation you already got, so you're going to just put this equation here using arraywise operation, and that's it. It's going to calculate h of ej omega, because you have already defined that z is equal to ej omega. And then you're going to calculate the magnitude response and phase response. Now, if I ask you that you have to show the expressions for magnitude response and phase response, then what you're going to do, you are going to go ahead first of all and write down h of ej omega. Right? You're going to go ahead and plug in z is equal to ej omega, so you're going to get this. From this, you are going to use Euler's identity, which is e to the power plus minus j omega is cosine omega plus minus j sine omega. So you're going to use Euler's identity and replace all the ej omegas by cosine omega plus j sine omega or minus j sine omega, based on if you're taking e to the power negative j omega or e to the power positive j omega. So I went ahead and replaced e to the power negative j omega by cosine omega minus j sine omega, and e to the power negative j2 omega by cosine 2 omega minus j sine 2 omega. And now you can separate out the real part of the complex number and the imaginary part of the complex number. So real part is 1 minus 0.8 cosine omega plus 0.5 cosine 2 omega. So that's your real part, that is your x, and plus j, and the imaginary part is of course negative j sine omega, negative j sine 2 omega. So I put let's see, oh, this negative is outside, so it becomes positive, negative, negative, positive. That's why I put a positive. So it's going to be positive 0.8 sine omega. So j is outside the bracket. So positive 0.8 sine omega and negative 0.5 sine 2 omega right here. So you have x plus jy. So if I ask you, you have to give me the magnitude response. First, you're going to determine this expression, and from this expression, you can write the magnitude response, square root of x square plus y square, and you can write the phase response, arctan of y over x. Right? But if you want to plot the response using MATLAB, you don't have to go through all this simplification. You just use the first equation and use that equation to plot the response, magnitude, and phase response. So again, it's extremely important that you understand, if I ask you to show me or give me the magnitude response equation and phase response, this is what you have to do. Alright, so the example continues with the plot, and this plot is a regular plot, it's not a decibel plot. If you want to plot the magnitude in decibel, which actually I'm asking you to do, I believe, in the project 4. So all you have to do is, you have the magnitude, m is equal to, So the absolute value of ej omega in decibel, as we discussed earlier, that is going to be 20 log 10 of h of ej omega, magnitude of that. That's going to be the decibel response. So I'm plotting the regular response, not decibel response, versus frequency in hertz, and I'm going up to fs by 2 because fs was 8000, so fs by 2 is 4000. And from this response you can see it is a high pass filter because low frequencies are suppressed and high frequencies are let go. Alright, next example, 6.9. Again, a difference equation is given to you, and the first thing that you observe is that you have the previous instance of y, hence it is an IIR filter, infinite impulse response filter. And from that filter, again, you are going to go ahead and put down h of z. From that h of z, if you're plotting, then all you need is this. But if you want to determine the magnitude equation and the phase equation, then of course you have to go ahead and plug in z is equal to e to the power j omega, and then from there you will take the simplify it using Euler's identity as I'm showing you over here, and then finally you're going to write the magnitude response of this complex number and the phase response of the complex number. And then you're going to go ahead and plot that versus frequency, and again from the response it looks like a high pass filter. And in the next video we're going to discuss basic type of filtering.